Now, the next thing we need to do is we'll need to check our analyte for non-specific binding. So once you've chosen your sensor chemistry and prepared your buffers, the very first test you should be starting with is a control test. And this control test is going to check your analyte for non-specific binding. So non-specific binding is when your analyte binds to something other than the ligand, often the sensor surface itself. And this is going to result in a false positive signal, which we don't want to have during the specific binding test. Now, there are a few ways to test for this non-specific binding. The most common option is to start by introducing the analyte over the initial sensor surface without the ligand present to see if we can measure any false positive signals. Now, the surface may be untreated, activated and blocked, or prepared with an inactive protein to mimic the physical properties of the active surface. So examples would be if you're performing non-specific binding on a carboxyl surface, you're going to want to activate it with EDC NHS and then block it with your blocking solution. Whereas for your NTA surface, you're going to want to block that surface by immobilizing a histidine tag protein that would be considered inactive or won't bind to your analyte so that you can mimic the physical properties of your active protein. And then if you're using a streptavidin surface, this can be left untreated as the streptavidin itself will act as a blocker on the surface. Now, when running these tests, ideally you want to see no response from your analyte interacting with the sensor surface. However, if you do see a false positive binding signal, this is actually okay and actually very common, especially when working with a simple buffer solution such as PBS or HBS. And this is going to be the first point of experimental optimization. So what we have here now is just an example of how to block a carboxyl sensor surface. As I mentioned, you're going to start with activating the surface with EDC NHS, and then you're going to skip the ligand immobilization step and then inject just your blocking solution to block the sensor surface. Now for a one-channel system, this is done on a separate sensor, whereas for a two-channel system, this is done in the reference channel. To reduce these non-specific binding signals, if you were to see any, again, this will be done by optimizing your buffer conditions, namely by including a variety of different buffer additives. And this is a standard technique across all SPR experiments, and it's not only unique to our instrument. So what I have listed here are the most commonly used buffer additives. For example, tween 20, which is also referred to as P20, can be included to help reduce hydrophobic mediated nonspecific binding. BSA is a protein additive that is commonly used. Or if you suspect the interaction is more electrostatic mediated, you can add additional salt or adjust the pH of your running buffer. Now, the literature is a great resource for looking at starting buffer conditions. But note that the surface coating on sensors from different companies will vary, so we highly recommend testing specifically on our sensors. And ideally, you only want to proceed to your specific binding test once you reduce the non-specific binding as much as possible. So to continue that example of blocking on the carboxyl sensor to test for non-specific binding, what you will then do is inject your analyte starting with your normal buffer condition, which in this case would be our plus 0.005% tween. And then you're going to add different buffer additives to see if we can reduce the signal of our analyte on the block sensor. And as you can see from this example on the right, the curve in green, which has 0.05% tween and 0.1% BSA added, has reduced the nonspecific binding to 0. So these are the conditions that you will now add to your running buffer and your analyte samples for your specific tests.